So we said that we can perform several linkage transformation, and one of them is through the cam follower system. We can see that the cam follower system is another transformation of the 4-bar linkage system. Let us do the interpretation how we transform the 4-bar linkage in order to get the cam follower. So for the 4-bar linkage system, we have 4 links, okay, connected through revolute joints, and one of these links constitutes the ground. So here you have 1, 2, 3, 4 links. Okay. Now, what did we do to get the cam follower? First, here all joints are of revolute type. However, with the cam follower, the connection between the cam and the follower is not a full joint, it's a half joint, because we have the possibility of rolling and sliding at this level. This is why we say that the first transformation from 4-bar linkage to cam follower system is the replacement of a full joint by a half joint. And this is, if you remember, was strategy number 2. Okay, so one of the strategies of transformation is to replace a full joint by a half joint. The second strategy is to remove a link. So here, for the cam follower, if you count the number of links, you have the ground is the first, the cam is the second, and the follower is the third. So you have only 3 links compared to 4 links for the 4-bar linkage system. So the second strategy was to remove a link. So here we did 2 transformation, number 2 and number 3. And we said that the combination of these 2 strategies will lead to strategy 4 that will not change the degree of freedom, because we have seen that strategy 2, which consists on replacing a full joint by a half joint, will add the degree of freedom by 1. However, the removal of a link from the system will reduce the degree of freedom by 1. So in total, when you combine these 2 strategies, you don't have a change in the degree of freedom. So you expect that your cam follower system will have a degree of freedom equal to 1, and we'll see together that we can make an analogy between it and between the 4-bar linkage system. How we can make this analogy? To make the analogy, we can try to identify effective links. What do we mean by effective links? So as we said previously, an effective link is a link that is not physically present, but we have the same effect as it was here. Okay, so for example, if you look at the figure here, what do you have? You have that because of the contact line between follower, you have a force that will be transmitted perpendicularly to this contact line. You know that for any 2 surfaces in contact, you have a transmission of force in the perpendicular direction to the contact line. So we can say that the force is transmitted between the cam and follower through this line. So it's like if we have a certain effective link here joining the 2 parts. Okay, so you will have like an effective link where the force will be transmitted through the line of contact, and you have links to 2 links to the ground. So this is equivalent to a 4-bar linkage, but the difference is that this link here is of variable lengths, because if you consider a new position of your cam follower, you know that what will happen for each position, you have if you draw your contact line here, okay, and you consider, let's say, the intersection between 2 lines of your cam and follower with the contact line, you will have 2 new points. Okay, so the idea is, let me observe 1 line of the cam, and let me observe one line of the follower, and I can identify for each angle of the cam a certain position for the line of the follower, and then for each instant I can draw the contact line. And because the profile of the cam is varying, then the contact line direction will vary, and also the distance between the 2 intersection points with the line of cam and follower will have a different distance between them. So this is similar to a 4-bar linkage, but it has a certain property that the effective link L3, which is the coupler, is of variable length. Okay. Now, this is about linkage transformations. Now we will start to define different intermittent motions. Okay. What is the idea of intermittent motion? Intermittent motion is when I can cause a sequence of motions and dwells in a certain mechanism. What do we mean by a dwell? When we say dwell, this means that for a certain period of time, my follower is not moving. Okay. And how can I produce this? I have several possibilities. The first strategy is to use a cam follower system. How can I induce a dwell for my follower? The idea is to understand how the cam follower operates. The operation of cam follower system rely on the variation of this distance. Okay, because you can for the cam you can provide any profile, and this profile is characterized by a changing distance between the fixed point of rotation and the different points of your cam. Okay, so if you impose a certain curvature, yani for a certain part of your profile, if you impose a circular curvature, this means that for this part, when this part is in contact with the follower, the distance between the center of the cam and the follower will not change anymore. And what is causing the motion of the follower is this change in distance between the center of the cam and the contact point. So whenever, imagine that now you have rotation of your cam in this part, when it's rotating in this part and the follower is in contact with it, okay, since this distance is not changing when the cam is going through this part, okay, so this is your cam, this is your cam in this position. Okay, for this part, when the contact point is a part of the circle, then the distance is not changing, and this will cause a dwell for the follower. This means that whenever the contact point is a point of this circle, the follower will remain at the same place because this distance is not changing. The follower will continue to move when the point of contact will not be any more of this part. Then when you move to the changing distance profile, your follower will go to motion again. Okay, and you can cause a series of dwells for a cam follower system if you consider different curved part having a circular shape. And for example, you can do this. I have a circular shape here, then I have a variable profile, then I can have another circular shape, of course, yani, with respect to the center. So let's say this is the center, this is the first circular shape. Here you can cause another circular shape. Okay, so whenever the contact point is a part of the circular shape, you have a dwell for your follower. And whenever you go through variable distances, you change the profile, then you have motion of your follower. Okay, so this is the easiest type of intermittent motion you can create through a cam follower system. You have several other mechanisms, and to understand more these mechanisms, as I posted for you several YouTube links showing the simulation of these mechanisms. So please, if you didn't go over them, try to watch the videos. They will help you to understand what is happening. Okay, now I will explain the second type of mechanism that can induce intermittent motion, which is the Geneva wheel mechanism. Okay, so here in this mechanism, what is happening? This is the Geneva wheel. The Geneva wheel is characterized by the presence of slots within the wheel. Okay, and these slots will allow rotation of the wheel. How? What you are doing here, you have a crank system that is rotating continuously, but for the Geneva wheel, the effect of rotation of the crank will not be the same at any instant, because you will have some parts of motions and other of dwells of your Geneva wheel. How you can create this? The idea is that within your crank, you have two main parts. One part having a shape of a circle, and this circle will be for a certain period of time in contact with the Geneva wheel. Okay, and you have for other times, as your system is rotating, you have a point on the crank that will be able to move in the slots of your Geneva wheel. So let's say, for example, the crank is rotating. Okay, when this point will reach, when the point of the circle will reach this level, now you will have contact between the arc of circle and the Geneva wheel. And whenever you have a contact between the arc of circle and the Geneva wheel, if you do an analysis about the contact is of circular type. Okay, whenever you have a contact of circular type between the two, if you study the transmission of forces, okay, the transmission of forces, let's say, will be perpendicular to contact. Okay, so you have transmission of forces perpendicular to contact, and then what will happen is that if you want to find the net force transmitted from the crank part to the Geneva wheel, you will see that, so let's say this is the center of your Geneva wheel, okay, and you have this contact line between the arc and the Geneva wheel. Then what will happen is the following. You have that since forces are transmitted perpendicular to contact, when you want to find the resultant force transmitted, okay, the resultant force transmitted, let's say, if you divide it into components, into normal and tangential component, you will see that what do we mean by normal component? A normal component is directed towards the radius of rotation, okay, and a tangential component is directed, if you want, within in a direction perpendicular to the radius. Okay, when you do the summation, you will see that tangential components will cancel out, and you will only have a net normal component. And you know that if I apply a force on a rotating device passing by the center of rotation, I cannot produce any rotational effect. To be able to rotate my wheel, I should have a net component that is tangent to the radius. Okay, and since this is not happening when I have contact between the arc of circle and the Geneva wheel, then I will not be able to cause any couple, and I will not be able to cause rotation of my wheel. So once the contact between the two parts is through this line, okay, I will not have rotation of my wheel. I will only have rotation at the instant this point will enter the slot. Why? Because when this point will enter the slot, okay, and will move back and forth, then what will happen is that now the contact line is along a line perpendicular to the radius. So this is your center, this is the radius, okay. Now when this point will enter the slot, what will happen? The contact between the two is or within this line or within the second line. It depends on the direction of rotation. So for example, if I consider that my wheel is rotating like this, okay, so as my wheel rotates, this point will press on this part, so normal force will be perpendicular to this line, okay, and then what will happen is that I am creating a force that is perpendicular to the radius. So at a certain instant, whenever my point is within the slot, I will have that the couple created is the force of contact times the distance to the center. This force and distance will be variable, but I will be able to produce, whenever my point is within the slot, I am able to produce a couple, and this couple will lead to rotation. But this couple is variable. This is why the angular velocity of rotation of the Geneva wheel will be varying. We'll study this effect when we go to analysis of velocity, angular velocity variation, etc. So we'll relate the velocity, the angular velocity of the Geneva wheel to the angular velocity of the crank when we study the when we do position and velocity and acceleration analysis for mechanists. Okay, but for now you should understand that by this configuration I can cause intermittent motion, because when this point will go back and forth through the slot, I will have a couple transmitted to the wheel that will lead to its rotation. And when I have the case where the arc of circle is in contact with this part, I have no motion. Okay, and as you can see here, if you want to expect the direction of rotation, okay, all you have to do is to find your couple and do the analysis of the rotation of your wheel. Okay, now another type of intermittent motion is the following one, which consists on a ratchet wheel connected to two poles. You have one that is called the driving pole, which is this one. This is the driving pole. And you have another one which will play a locking effect when the arm will be reversed, which is this one. This is a locking pole. Okay, now how the system operates? It's very important to look at the video to see it in practically, to see the simulation. So I will try here to explain as much as possible. So what will happen is that your arm will have oscillatory motion. It will rotate back and forth. Okay, when it's moving in this direction, what will happen is that this driving pole will move through one tooth of your ratchet wheel. Okay, and this will happen also through the locking pole, because the locking pole will just have a locking effect in the reverse direction. But when your wheel is rotating like this, what will happen is that your locking pole will go over one tooth of your wheel, as the driving pole did. Okay, now when you reverse the arm motion, what will happen is that this driving pole will move backward, will try to move backward, but what will happen is that the locking pole will not allow the ratchet wheel to move. And just this mechanism will be able to go backward, but the wheel will stay in the same position, because you have a locking effect here. Due to the geometry of the pole, as you can see, the geometry of the pole will allow relative motion in this direction between the pole and the wheel, but not the opposite one, because when you move in the opposite direction, you have an obstruction. You have here an obstruction, a physical obstruction that is created by the geometry of the locking pole that will not allow the wheel to go backward. Okay, this is why we say that as we can create an intermittent motion for the ratchet wheel, because when the arm will move in this direction, the ratchet wheel can rotate. However, when the arm moves in the opposite direction, the locking pole will do a blocking effect and will not allow the wheel to move. Okay, you can see the simulation of this in the YouTube link I posted for you in the playlist. Yes, they are connected with springs to ground. Yes, it's right, Sam. Okay. Dear students, I know that the battery is low, but I'm working on 4G. Okay, because no electricity. So now let us consider another type of intermittent motion. So for another type of intermittent motion is through the following mechanism. The following mechanism is another type variation of Geneva mechanism. The idea here is similar to the Geneva wheel, but here I don't want to produce intermittent rotation. I want to produce intermittent translation. Okay, so to cause the intermittent translation, this is what I will do. I will design a certain mechanism connected to slots. Okay, and then my crank will be equipped with a point that can move through these slots back and forth. Okay, so then what will happen is the following. As this point, when your crank rotates, okay, you will have two periods. You have half of the period for which this point will be in contact with the slot. So it will go up first and then down. When this point will reach, if you want, the downward position, then your system will be moved from one location to the other one. So will move a certain distance. And then if I want to illustrate the new position here, this is the new position of your crank, and this is your point. The point now will be exiting the slot. Okay, so at this level, when theta equals 0, this point will enter the slot. When theta equals 180, the point will exit the slot, and the slider will then be able to move a certain distance. Now, in the second phase of rotation, this point is not in contact with the slot anymore. This is why for the other half of rotation, your system will not move. It will undergo a dwell. Okay, and this will be repeated in a periodic way, because when the system moves, this part will be now in this position, and it will wait for this point to come to again to this position to go back and forth, and this will be repeated several times. So this will cause intermittent translation. So your slider will move a certain distance, it will stop, then it will move another distance, etc. This is used a lot in industries. So we use it in industries for the purpose of displacing objects from one location to other. So let's say you have a production line. You want to stop your slider for a certain time to collect the products, and then you for another phase you want to move them to another location. Okay. So this is for intermittent motion. Now, another concept also illustrated in the videos